It's an urgent debate and a sensitive one. How does our atmosphere work? How and why is it changing? And how will it cope with what humans do over the next century? How should we intervene to avoid these problems? And how do we know we're giving valid answers to these questions when there are still so many surprises?
We were flying over pristine rainforest, measuring natural canopy emissions, and we found something rather surprising.
One would expect the concentration of hydroxyl radicals to be scarce in this environment. But what we did find was high concentrations, and this didn't conform to our computer simulations. We hadn't seen anything like this before. When this happens, it's an opportunity for the global atmospheric chemistry community to perform new experiments to reveal what's happening.
The hydroxyl radical can react with VOCs such as isoprene at different points on the molecule. The new radicals that are formed can follow multiple pathways, which rapidly leads to a complex mixture that is difficult to measure.
Experiments revealed a cascade of chemistry which led to adjustments to our computer models.
The hydroxyl radical acts like a detergent, cleaning the VOCs out of the air. Usually, a VOC reacts with the hydroxyl radical, essentially removing it. However, in the case of isoprene, it's proposed that it forms new hydroxyl radicals, essentially recycling it.
New and unexpected observations require a collaborative approach. We're bringing global expertise and technology together under one roof at the University of York, where we've built the first dedicated laboratory building in the UK for atmospheric chemistry research.
As a laboratory chemist, this new building helps me share ideas, experiences, and even equipment with the field measurement community, the aerosol scientists, the analytical chemists, and of course with the global modelers.
There are a huge number of chemical reactions in the atmosphere, many of which we don't understand. We're trying to recreate that chemistry in the lab. We use aerosol simulation chambers and instruments that we've developed here at York to understand the speed and the products that are formed from these reactions.
Field projects are devised alongside the researchers who will work with our data to develop and maintain computer models.
Long-term measurements help us validate simulations. All of our measurements are calibrated via common standards. The new facility provides a UK link to the global calibration scale.
To understand the mechanisms at work, York's researchers take to the land, sea and skies.
We have a research aircraft that's kitted out with state-of-the-art instrumentation, some of which is designed and built here in York, that we use to make atmospheric measurements all over the world.
York run part of an atmospheric observatory in Cape Verde, where we sample clean air, which is representative of a larger region. The site has minimal local influences to distract from the global picture. The observatory's coastal location allows measurements of gases emitted from the ocean.
How do the oceans influence our atmosphere? We found that reactive halogens can be emitted from the ocean surface and transported to the lower atmosphere. Here they can make significant contributions to the destruction of ozone.
The more data we collect, the more confidence we have in our atmospheric models.
Computer models represent our theoretical understanding of the Earth's atmosphere and the mechanics of its processes.
Models allow us to pull individual chemical levers. That allows us to ask what-if questions based on our raw field data.
Early career researchers are exposed to world-class scientists, cutting-edge methods, and opportunities on a global stage.
Our new facilities allow us to better train a new generation of atmospheric scientists.
My research involves the method development of an airborne gas chromatography mass spectrometer for use in fieldwork. I've been taking measurements on flights to Sweden, Guam, and Micronesia.
We'd like to develop a laboratory that has all the key components that you need for successful atmospheric chemistry research. That includes the ability to do lab experiments, to develop new instruments, and to make observations in the atmosphere.
Despite the known importance of isoprene emissions from forest environments, there are currently no seasonal long-term studies. We're developing a new gas chromatograph to measure isoprene in the Borneo rainforest. The data produced will be used to better test and constrain the model simulations.
These new labs will measure atmospheric free radical lifetimes, study how radicals are recycled in the atmosphere, and assess the impact of chlorine to air quality over the UK.
Our next mission is to London. Here we will make measurements of the emissions of air pollutants that will allow a better simulation of future UK air quality.
Physical science and the evidence we collect in this laboratory will be essential for supporting policy in the future.